Today we're learning how to graph rational functions, and this is taking everything from the entire unit and putting it on a graph.
To start with, let's review the lesson warm-up. You should be able to do this by yourself. It's everything we did during the last class, but I'll go through the answers quickly with you. So this function is given in standard form, both the numerator and the denominator. Because a lot of the parts require us to have factored form, I'm just going to go ahead and factor both the top and bottom of this fraction. The numerator is going to factor to x minus 4 times x plus 3. The denominator is already in its simplest factored form, so we're going to leave that as x plus 1. So I'm either going to use the standard form equation to answer the parts, or I'm going to use the factored form. To start with the domain would be found by setting the denominator equal to 0. The denominator is x plus 1. If we set that equal to 0, we know that x cannot equal negative 1. But remember that we always write our domain in interval notation, so negative infinity to negative 1 with a union negative 1 to positive infinity. The x-intercepts are found by the factored numerator after you get rid of any common factors. This expression does not have any common factors, so we're going to set each factor in the numerator equal to 0. That's going to tell us that x equals positive 4 and x equals negative 3. When you write your x-intercepts, we write them as ordered pairs, so negative 3 comma 0, 4 comma 0. Those would be points on the coordinate plane. The y-intercept is going to be determined from the standard form equation, and that's found when you substitute x equals 0 into the original function. When you substitute x equals 0, you have a solution of negative 12 over positive 1, which simplifies to negative 12. So 0 comma negative 12 is your y-intercept. For the wholes, there are no common factors, so there are no wholes. The vertical asymptote is determined by the remaining denominator after you get rid of common factors. Of course, there are no common factors, so the denominator set equal to 0 is x equals negative 1. That is your vertical asymptote. Remember that vertical asymptote is x equals, horizontal is y equals, oblique is also y equals. You're going to have one or the other of these last two. All right, horizontal asymptote is determined by the degree in standard form. So we need to look at our standard form equation. The largest degree of the denominator is 1. So recall that we have a numerator of degree 2, denominator of degree 1. If your numerator degree is larger than your denominator degree, then you have no horizontal asymptote. And if you have no horizontal asymptote, for the problems that we're doing, that indicates we're going to have an oblique asymptote. Oblique asymptotes occur when the denominator degree is 1 less than the numerator. Only 1 less. When you use oblique, or when you find the oblique asymptote, you use your standard form equation. Your numerator is your dividend, so this goes underneath your division symbol. Your denominator is your divisor. And remember, you're only looking for the quotient, so we don't actually care what the remainder is here. X squared divided by x would give us x. This would give us x squared plus x. We're subtracting both terms. X squared minus x squared is 0. Negative x minus x is negative 2x. Bring down the negative 12. Now we have negative 2x divided by x, which leaves us with negative 2. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. Okay, we actually don't need to continue because we don't care what the denominator is. We are only looking for this quotient. So the quotient, or the answer, is also considered the oblique asymptote. So we would write the oblique asymptote as y equals x minus 2. And that was your quotient from your division problem. So just briefly, I'm going to use a highlighter to indicate which ones go with which. So factored form will highlight in yellow. Domain comes from factored form. X-intercepts comes from factored form. Holes come from factored form. Vertical asymptote comes from factored form. Next, I'll highlight standard form. We'll use blue for this one. The y-intercept is determined from standard form. Horizontal and oblique asymptote both come from standard form. If we scroll down this next section here, these are just pre-done graphs, so you have them as a reference. Each one of them includes the function, so you can look back and you can see what the function is and what the graph looks like. I'm not going to talk about all of them. I just want to make a quick note with this, so kind of add to the directions. If we look at this function, we can see that we have an oblique asymptote here. Then we have two vertical asymptotes. So the definition of an asymptote says that a function approaches it but never touches or crosses. But if we zoom in on this graph and we look at the center right here, you can see this line cuts right through that asymptote. So it's intersecting the asymptote at this point right here, which based on the definition that we've previously gone over, that cannot happen. So this actually, there's a special rule for this. This is the only time it can happen. So a graph can cross or intersect a horizontal or oblique asymptote only when it is between two vertical asymptotes. So because there is two vertical asymptotes and there's this center, it can in fact cross the asymptote. That is the only time that happens. So here we can review the steps of graphing a rational function. The first step is going to be to find the domain. The second step is going to be to find and sketch the holes and asymptotes. That would include the hole, vertical asymptote, horizontal, or oblique asymptote. Next, find and plot the x-intercept and y-intercept. Lastly, we're going to find and plot at least one point in the test interval determined by any x-intercepts and vertical asymptotes. For the first function, this function is given to us in standard form. So let's take a moment and factor this just so we can use the factored expression for certain parts. And actually before I factor both of them, notice that the denominator of negative 4x squared minus 16x minus 12 does have a common factor of negative 4. So I'm going to factor that out just to start with, and then I'll factor both expressions. Okay, so knowing that that has a GCF, that's going to allow me to now factor completely. The numerator is going to factor to x plus 3 times x minus 2. And the denominator has that GCF of negative 4. And then the remaining denominator factors to x plus 3 times x plus 1. Okay, I'm actually going to go one step further and I'm just going to identify that there's a common factor and I'm going to eliminate that now. That way I have all three expressions. I have my standard form, my factored form, and then I'll have my simplified form. So here we have our common factor. Eventually we would eliminate that, especially when we're finding the wholes. So our factored form is going to be x minus 2 in the numerator divided by 4 times x plus 1. All right, I'll label all of these for you. Okay, based on the direction, step 1 is to find the domain. The domain is from the denominator in factored form. And we set this equal to 0 and we solve. So if we were to set the denominator of negative 4 times x plus 3 times x plus 1 equal to 0, we would have a 0 at x equals negative 3 and x equals negative 1. Both of these values have to be omitted, so the domain is going to be negative infinity to negative 3 to negative 1, negative 1 to positive infinity. Okay, next we need to find and sketch wholes and asymptotes. So I'm going to start by finding the wholes. And actually, we found the 3 forms above, so we already found standard form, factored form, and the simplified form. So hopefully you all recognize that we have a common factor of x plus 3. We can eliminate that common factor. Eliminating the common factor tells us that the x value is going to be found by setting that common factor of x plus 3 equal to 0. X is equal to negative 3. And then once we substitute x equals negative 3 into the simplified form, so we'll substitute x equals negative 3 into this form, that's going to give us the y value. So y is found by negative 3 minus 2 divided by negative 4 multiplied by negative 3 plus 1. This is equal to negative 5 divided by negative 4 times negative 2, which is positive 8. So negative 5 over 8 is your y value. That tells us that the whole is at negative 3 comma negative 5 over 8. Okay, once we find the whole, the next thing that we need to find is going to be our vertical asymptote. And the vertical asymptote is found by setting the remaining denominator in the simplified form. So whatever's left from the simplified form, setting that denominator equal to 0. Negative 4 multiplied by x plus 1 equals 0. Divide both sides by negative 4. X plus 1 equals 0 over 4, or 0. X is equal to negative 1. That's your vertical asymptote. Next, we'll find our horizontal asymptote. The horizontal asymptote is always found by looking at your standard form. And from standard form, you look at the degree of the function. In this case, the degree is the same for both the numerator and the denominator. So you set up a fraction, y equals, it's the leading coefficient of the numerator, which is 1, over the leading coefficient of the denominator, which is -4 in standard form. So the horizontal asymptote is at -1/4. And if you have a horizontal asymptote, then automatically you know you don't have an oblique. You only have one or the other. So to find the oblique asymptote, in this case, there would just be none.
Now we're going to sketch all the parts we just found in step 2. So let's start by sketching the hole on the graph, which is located at -3, -5/8. This is going to be a hole in the graph, so graph it just like you would graph a hole. -3, -5/8 is located somewhere in that area. It is just a sketch, so be as accurate as possible, but you don't need to be over the top precise. The vertical asymptote is located at x equals -1. So I'm going to sketch a vertical line at x equals -1. The horizontal asymptote is located at y equals -1/4. So I'm going to sketch a horizontal line at -1/4. And next, I'm not going to graph anything for the oblique asymptote. Obviously, we do not have anything. Step 3 is to find the x and y intercepts. We'll start with the x-intercept. The x-intercept is identified by the simplified form. And within the simplified form, you're looking at just the numerator. You're going to set the numerator equal to 0, and you're going to solve for x. In this case, x equals -2, which indicates the x-intercept is at 2, 0. I think I said -2. It's at +2. Next, we find the y-intercept. That's when you substitute 0 into the standard form for x. When we do that, in this case, we are left with -6 over -12, which simplifies to +1/2. Our y-intercept is at 0, 1/2. Okay, next we have to graph these 2 points. So I'm going to plot a point at 2, 0, and I'm going to plot another point at 0, 1/2. So I'm going to ask that everyone has at least 2 points on each curve. There's some things that you'll notice when you start to graph a lot of these functions. So if you have a graph like this where you have just one horizontal, one vertical asymptote, you're going to have graphs that fall in the opposite locations of each other. So I'm going to sketch this graph here in the upper right corner. It's going to come down, it touches both points, and it continues. It never touches or crosses that x-axis. So this here is the curve in the upper right corner of my rational function. If you have a graph in this area up here, then you're always going to have something in this area here, which is why you see the hole in that area. And that's it. You'll have opposite, so diagonal graphs. So on the other side, if you had a graph in this section, then your other graph would be here. They're always diagonal from each other. This happens when you are graphing with both one horizontal and one vertical asymptote. So I think just 2 points is enough for you to see the curve. And when I say 2 points, you're looking at 2 points right here, because obviously you have those 2 points and then you also have the asymptotes that you can kind of hug close to but never touch or cross. So if we look at this other interval, sorry about that, go ahead and count that hole as a point just for like graphing purposes. Obviously it is a hole, not a point, but it gives you a location. So just pick one other value in this test interval, so somewhere in this area. Pick one other x value, test it in the original function, and find your y coordinate. So I'm going to test x equals -2. That would be right here. So somewhere on that line, there's going to be a point. When you substitute this into the original function, you have -2 squared plus -2 minus 6. And this is over -4 times -2 squared minus 16 times -2 minus 12. Our numerator simplifies to 4 minus 2 minus 6 divided by -16 minus 30, plus 32 minus 12. This simplifies again to -4 over 4, which is -1. That indicates that we have a point at x equals -2, y equals -1. When I plot that point is located right here. Now we have 2 points, one of them being a hole, but enough for us to graph our curve in the coordinate plane. And our final graph looks like this. Okay, so where does the domain fall in? Because that was step 1. So what exactly does the domain mean? So the domain is looking at your x values, and I'm going to use, let's use a blue highlighter for this. So the domain, when we scroll up, should match starting at -infinity, heading towards positive infinity. As we move this way, we have all x values, and then all of a sudden we have a hole, so the graph stops, or our domain stops right there at the hole. Then it picks up again until our vertical asymptote. Then it starts again after the vertical asymptote and goes on forever. So according to our graph, our domain should be from -infinity to -3, and then again from -3, which is the hole, to this line here, which is our vertical asymptote at -1, and then again from -1 to positive infinity. So just compare this to what you already found for the domain, and you can see it's exactly the same. So that is correct. But you should always check the domain. Values that you omit in the domain are holes and vertical asymptotes. Okay, let's do number 2 together, and then you can do the on your own by yourselves. Number 2 is x squared minus 4 over x. This is called the standard form. Next, let's write this in factored form. Factored form is equal to x plus 2 times x minus 2 divided by x. And there is no simplified form of this. There is nothing that cancels, so factored form is where we're going to stop. The domain is setting the denominator equal to 0. In this case, x cannot equal 0. So the domain is -infinity to 0 with a union 0 to positive infinity. Next, we need to find the holes and asymptotes. So holes are found when you have a common factor, In this case, we don't have any common factors, so there are no holes, or I'll just say not available. The vertical asymptote is found by setting the remaining denominator equal to 0. In this case, x is equal to 0. The horizontal asymptote is identified by the degree of the function in standard form. It looks like the degree of this function, the numerator is 1 more than the denominator, so that indicates that there is no horizontal asymptote, but it does tell us that there's an oblique asymptote. For the oblique asymptote, underneath our division sign, we are going to have the numerator of the function, which is x squared plus 0x minus 4. On the outside, we have our divisor, which is just x. Looking at the first terms, x squared times x is just x. X times x is x squared. We are subtracting this value. X squared minus x squared is 0. Bring down 0x. And in this case, we would have to find what term 0x divided by x would be left over for the quotient, and the answer would be 0. Of course, you could multiply this out, but we are only looking for the quotient. We don't care about the denominator. So our oblique asymptote is at y equals x plus 0. Down to the graph. At this point, all we have to graph is our vertical asymptote at 0. And an oblique asymptote at y equals x plus 0. That means the y-intercept is up at 0, and you go up 1 over 1 for the slope, or down 1 over 1 for the slope. Oblique asymptotes are always slanted lines in the coordinate plane. So we're going to have two curves. We're either going to have, well, I'll just tell you because I know, but you're going to have a curve here and here in this one, but your other options would be here and here. So always diagonal curves. And like I said, this one is going to be up here and up here. I know you guys wouldn't know that. I'm just telling you because I do know what this graph looks like. Just remember that they're going to be opposites of each other. So finding the x-intercept, to start with, the x-intercept is found by setting your numerator equal to 0. So we have x plus 2 equals 0, giving us x equals negative 2. And we have x minus 2 equals 0, giving us x equals positive 2. So we have two x-intercepts, one at negative 2, 0, one at positive 2, 0. Next, let's look at the y-intercept. The y-intercept is found by the standard form, substituting 0 in for x. You end up with negative 4 over 0. If that's the case, then you would have no y-intercept. It is undefined. You cannot have a 0 in the denominator. So at this point, all we are graphing is our x-intercepts at negative 2 and positive 2. We do not have a y-intercept. So like I mentioned, we only have a curve up here and here. We have 1 point in each of those intervals, so we're going to need to test for a couple more points on that curve. Let's start with something in this area. So you need to pick points that are close to negative 2. So pick maybe negative 3, negative 4, or negative 1 if you want to. So I already tested these values just so that we could save some time. So let's test when x is equal to -1. If this is the case, your output, f of -1, is equal to 3. So this would give you an ordered pair at -1, -1 comma 3. I also tested let's see, -3, just in case you wanted to do that one instead. So when you test -3, you end up with an output of -1.67. So your other ordered pair would be at -3, comma, -1.67. And you should try testing these on your own just to make sure you're coming up with the same answers as me. So when I plot these, -1, 3 is located right here, and -3, 1.67 is located here. When I sketch the line, it hugs along the asymptotes, never touches or crosses them, and it touches both of, or all three of those points in this case. So next I need to test points somewhere in this area, so either +1, 3, or 4. I'm going to show you when x is equal to 1 and you substitute that into the original function, your output is at -3. That gives you an ordered pair at 1, comma, -3. And I also tested when x is equal to 3. Substitute this into the function. Your output is 1.67, which gives you an ordered pair at 3, comma, 1.67. If I plot these points, I have a point at 1, -3, and another point at 3, 1.67. For my second curve that hugs along the asymptotes, never touches or crosses, and it looks like this. So this is your final graph. This graph has both a vertical and an oblique asymptote. The on your own graphs are posted on my website if you would like to see the answer key, and let me know if anyone has any questions.